Congruences are very important in number theory, and we'll be going very deep into them, but right now we'll just look at what they are. So in this box I've written how you write congruences in symbolic form. This reads A is congruent to B modulo C. And this is the congruent sign. It's just 3 bars on top of each other. It's right there. So what this means is that if you take A minus B divided by C, it's going to be an integer. So I played with that statement a little bit and I went down and my final result was this, which is just an expression of Euclid's division lemma. So what most people know this statement as is if you take A and divide it by C, then the remainder is B. So for example, if you take 6 is congruent to 2 mod 4 because 6 divided by 4 gives remainder 2. So we're just going to go into some properties of congruences right now. This is the first property. It says that A is congruent to A mod C. That's obvious because A minus A is 0 and 0 divided by C is an integer, which is 0. So the next one we'll look at is this one, which says that if A is congruent to B mod C and B is congruent to D mod C, then A is congruent to D mod C. And we can see that because A minus B over C is an integer, B minus D over C is an integer. And if we add these two statements, then we get A minus D over C, and we get an integer plus integer, which is integer. So that works out. These are a few other properties of congruences. So this one we have if A is congruent to A prime mod C and B is congruent to B prime mod C, then the first one we have is that A plus B is congruent to A prime plus B prime mod C. And to prove that, we just take this statement and subtract. So A plus B minus A prime plus B prime divided by C, and that's an element of integers. And we just break this up. So we group the A and the A prime and the B and the B prime, and we get these. And these we know are integers because of these two statements up here. And this works if you put a minus in between here as well. And this is going to be our number 4. This one says that AB is congruent to A prime B prime modulo C. And so that's what that means. And we see that if we come down here, to prove this, I added and subtracted a similar term. I think I did this on a separate piece of paper. So this is what that means. I added and subtracted a similar term. So I had AB and A prime B prime from here. I added and subtracted A B prime. And then I grouped. And so I grouped this term and this term right here into this term. And then I grouped second term and the fourth term into this term. And we know that this is an integer because of our initial congruences, which was on this sheet right here, because of these initial congruences. And we know this is an integer for the same reasons, and this was defined to be an integer, and this was defined to be an integer. So they're all integers, we're just multiplying and adding them, so we get in the end an integer, and that is true. And the last property is the cancellation law, which is, this deals with multiplication. The cancellation law deals with division. So we come down here, we see that 6 is congruent to 24 modulo 18, but that does not hold if we just divide each side by 6. 1 is not congruent to 4 modulo 18. So we have to use the cancellation law because a certain condition has to be met. So cancellation law says that if BD is congruent to BD prime mod C and the greatest common divisor of B and C is 1, only then does D is congruent to D prime mod C. And to prove that, up here I just proved in this little box, because if we take this statement and we write it in the division form, we get this, and then we can factor it, but that means that C is either a factor of B or D minus D prime. We don't know which one, and that's what causes the confusion. So just to make it clear, if greatest common divisor of B and C is 1, then C can't divide B, so C has to divide D minus D prime, which gives rise to this statement. Those are properties of mods, and we'll go deeper into the next videos.